Welcome to another all explained video in which we will see the beauty of geometry and we will prove a very interesting trigonometric identity. But first, let's see how do we prove Pythagoras theorem. What is the proof of Pythagoras theorem? So this is the proof which I saw when I was a kid, and it goes like this. So suppose that this is a square, and then there are points on the edges of the square which divides the edge length into two lengths. Let's say that L and B. So you divide all these edges in the same order like this with L and B lengths, and then you join these points. Then you get possibly another square. It looks like a square, but we'll have to prove it. How are we going to prove it? So let's think about these four triangles here. 1, 2, 3, 4. So these triangles are congruent. They seem like congruent, but using SAS, side angle side criterion, you can prove that they are actually congruent, because you see these triangle number 1 and 2. This length and this length, they are same. This length and this length, they are also same. And the angle between here is 90 degree between these two lengths. So I'm not doing ASS, which is not a criterion for congruency. I am doing SAS, which is a criterion for congruency, and there can be proofs for this also, which you can think about. Okay, so now we are going to state something very interesting. We are going to say that the whole is the sum of the parts. And using that, we will derive our Pythagoras theorem. So first think about this whole area of the square in terms of L and B only. So you can say that this all the edge lengths are L plus B. You see this length and this length. This is the edge length, and you can square the edge length to get the area of the square. So that area is L plus B squared. Now we are going to calculate the area using the parts. So this part here is a square. Let's say that its edge length is h. So that we will get our Pythagoras theorem in its usual symbols. Let's say that this edge length is h. So all these lengths will be h, and this area would be h squared. And then we can think about the area of these four triangles here. Let's say that these areas are A. They are congruent triangles, so these areas will be equal. And the area of a triangle you can calculate by half into base into height. That comes from the area of a parallelogram, which comes from the area of a rectangle, and which is the area of a rectangle is actually the definition, the basic definition through which we calculate area. So I'm not going to go into that. I suppose you know about this area of a triangle being half into base into height. So half into base into height, you can take any of this length B or L as base or height because they are perpendicular. So area of one of these triangles is going to be half into LB. So then you can state this logical simple that whole is the sum of the parts. So you have the whole area of the square, which will be the sum of these parts. This inside square, the blue square inside the blue lines, and these four triangles. So let's equate these areas. So you get for this L plus B squared, for this area you get h squared, and for 4 times this area will be 2LB. And then you open up this A plus B squared, BA squared plus B squared plus 2LB, and 2LB will cancel out, and then you will get your Pythagoras theorem. So pretty interesting that Pythagoras theorem is logically, it's only stating that whole is the sum of its parts. So let's now go into this identity sine of A plus B, and this is equal to sine A cos B plus cos A sin B, and its proof, it's very interesting. When I was in high school, I used to get stuck between in the proof. So then I decided, now I decided to look at it in a different way, and taking inspiration from that geometrical visual proof of Pythagoras theorem, I would like to present in front of you another very beautiful proof using the areas. Let's go into it. So suppose we have this circle here, this is a horizontal line, and from here I mark an angle A. Okay, so first let's think about this length here. This length here, let's say that the circle is of a unit radius. So radius of the circle, this is a unit circle, you can say. So things will be easier with unit circle. Radius is 1, okay. So this length is 1. And if you look at this right angle triangle, then you can figure out that if you know that this is 1, this is hypotenuse, then you can figure out that the perpendicular is going to be sine A, right? And the base of this right angle triangle is going to be 1 into cos A, which will be cos A. Okay, then let's mark some lines, put these markings away because we can see clearly what is happening. Then I am going to mark this angle B here, and then again we will mark these lengths sine B and cos B. So cos B will be this base, and sine B will be this perpendicular. Great. So we have these lengths, and we are going to join this line also. Take a look at this, where the two rays which are making angle A and B are intersecting the circle. We are going to join that point. And first let's think about this. This is not a square, this is a rectangle. So let's think about this rectangle. What is the length of this rectangle? It's only cos B, and the height of this rectangle is sine A plus cos B. Okay, so what will be this whole area? It's very simple. Area of this whole rectangle is cos B times sine A plus sine B. Great. Now we are going to divide this area into parts and somehow introduce sine of A plus B. How are we going to do that? Let's think about this triangle. It's a very interesting triangle here. It's an isosceles triangle, right? Because this length is 1, this length is 1, because we are in unit circle. So these lengths are equal. So that's not that important. What is important is what is the length of this line. So here this length is 1, and we are taking a perpendicular. Okay, so this line is perpendicular. So we want to know the height of this triangle. What is the height of this triangle? So if this is 1, this whole angle is sine A plus B, and using the definition of sine, which is sine is P perpendicular by hypotenuse, you can calculate this perpendicular, and that would be sine A plus B. So we have introduced sine A plus B here. Okay, so what will be the area of this triangle? So this length was also 1. Okay, and this can be taken, 1 can be taken as the base of this triangle, and sine A plus B can be taken as height. So its area would be half sine A plus B. And then we can think about these 3 triangles here. So this is the first one, which is like this here. This is the second one, which is here, and the third one is a little bit complicated, and it's here. So let's think about the area of these triangles. So for the first one, what is if you take this as a base, what is this length? So this is cos A, isn't it? You can match it from here, cos A. This is the same length, and this length is sine A. So the area of this triangle is going to be half into sine A cos A. Okay, how about the second triangle, which is here? So you can figure out that this time you have, if you take the base as cos B, the height is sine B. So, okay. Then we have got this area to calculate, the third triangle. Its base length is a little bit difficult to see. It's cos B minus cos A. Look at this length here. This length here is the base of this triangle, and the height is the sum of sine A and sine B, as you can see here, from here to here, right? So then the area of this triangle is going to be this. And believe me, if we write that if we use the simple logical idea that the whole area is the sum of the parts of the area of the parts, then we will get our identity. So let's see, these are the parts and this is the whole. Okay, so let's see, let's rearrange stuffs. Okay, and then expand. So cos B sin A, cos B sin B, and you see half of sin A plus B and all these things here. And you can check it. Many things will cancel out, like the sin B cos B term is getting cancelled out, and similarly sin A cos A term will also get cancelled out, and you will be remaining with this thing, and then you can cancel out half, and you can very simply see that sin A plus B is sin A cos B plus cos B sin A. So yeah, so this thing also is basically saying that whole is the sum of parts. So this is a visual proof, and then we can go into some other proofs also for people who would like to see, like there is one very famous textbook proof in India, so I would also go with that proof, and then I will also go into another proof of this relation. So but this is what I want to show in this video. This is what I worked upon. So if you're here, thank you for watching. The next parts could be a little bit boring, so let's go into that. The second method. The second method, to understand the second method, you need to use this idea that suppose you have a right angle triangle and these three right angle triangles, and you know this angle is theta, and then if you know that the hypotenuse is of h length, then you should be able to write these two lengths very easily. Similarly, if you are given b and theta, you should be able to write these lengths very easily. Otherwise this textbook proof will look very cumbersome to you. And similarly in the last case also, you should be able to write these two lengths quickly. So let's first figure it out what these lengths would be. For this h we have already done with the unit circle in the last part, that you can use sin theta as p by h, and then you can figure out that p is h sin theta. So using such kind of trigonometric ratios, you can figure out these lengths. For example, here only if you use cos theta, you will get this base length to be h cos theta. So what about here? Take your time. What would be this length and this length? So you can use cos theta, and cos theta will be base by hypotenuse, and hypotenuse will be b by cos theta, which will be b sec theta, right? And similarly you can figure out that this will be b tan theta. You see these things, sin theta appearing here, cos theta appearing here. I would like to remind you that sin square theta plus cos square theta is equal to 1. This is also Pythagoras theorem stated in a trigonometric way. And also here you see sec square theta minus tan square theta is equal to 1. This is also Pythagoras theorem stated in it with sec and tan. And the third one, I think you remember from high school or not, cosec square theta minus cot square theta is going to be 1. So here you will get these two trigonometric ratios. For hypotenuse you will get L cosec theta, and for base you will get L cot theta. So if you know that, then you can feel the other proof is not so difficult. So this proof goes like this. You have this circle, it's again a unit circle, and you have this length A, and then you draw these lines, and you think about this length is going to be sin A, and then the base is going to be cos A. Okay, and then A plus B you are going to do here like this. You can make B angle here, this angle as B on top of A, and then you can figure out the base and height of the base and perpendicular of these two lengths. You can figure out, because this length is 1, you can again break it down. You know the hypotenuse, so the perpendicular will be the base will be cos B and the perpendicular will be sin B. Okay, so you know that, and then you can join this line. So here you get a triangle. This triangle I can mark as O, let's say AB. In this triangle you have this angle as A plus B, and this is again 1. This length OA is 1, so you can break it down this length, this whole length of this black line is going to be sine of a plus b, right? And this this part here, this small length here, is going to be cos of a plus b. So I have not written cos of a plus b here because that's not required in the proof. But now let's go into this proof. We have to prove that this length. So this proof is based on length. So this is also visual in a way, but you don't get to see areas here. You will get to see lengths. So you are going to prove that this length, okay, this length right here is sine a cos b plus cos a sine b. How are you going to do it? First of all, let's realize some important angles here. This angle is definitely 90 degree. So what would be this angle? 90 degree minus a. Then vertically opposite angle 90 degree minus a. Then in this smaller triangle right here, if you have this 90 degree minus a, 90 degree, what will be this angle? Think about it. This will be definitely a. So you have got some important angles here. And then what we are going to do, we are going to think of this black line as the sum of these two lines. Then again, in terms of length also, we are stating that the whole is the sum of its parts. Pretty interesting. And let's think about this red length. What would be this red length? So you see, you have in this right angle triangle, this one, I can mark it as A, B, C. You know the perpendicular. No, this is the base. This is the base according to this angle A here. You know the base. Then the hypotenuse should be in terms of sec A, right? Sin B sec A. So this will be sin B sec A. How about the base of this triangle? Let's move this. This is cos B. How about the base BC here? I will write it here. The base BC will be in terms of tan A. You see, this is the sec A tan A pair. So sin B tan A. Okay. Then we have calculated the red length. Now we should calculate this blue length. How to calculate this blue length? You see this slant length here. Let's call this O and this as M and this as N. So if you can figure out this ON length, then you can figure out this blue length also from this smaller right angle triangle here. So what is this length ON? So you know OM, which is cos B. You know MN, which is sin B tan A. So ON is going to be the difference of these two lengths, cos B minus sin B tan A. And now in the smaller triangle, you know the hypotenuse. This is hypotenuse, and you want to know the perpendicular. Then you only have to multiply sine of the angle here, which is A. So you have to multiply sine A. So this length is cos B minus sin B tan A. So this length will be sin A times this length. Okay. And now we just have to use the idea that whole is the sum of its parts. So these two parts, if we add these two parts, let's add them. What do we get? This will be equal to sin A plus B, of course. So what do we get here? You just have to simplify it a little bit. Sec A, I'm going to use cos A, 1 by cos A. Cos B, sin B tan A. You multiply sin A here, you get cos B sin A. You multiply sin A here, because tan A is sin A by cos A, you get a sin squared A here and cos A in the denominator. And then you see, you can club these two terms together and you can take sin B by cos A common. So you will get 1 minus sin square A and cos B sin A. 1 minus sin square A is definitely going to be cos square A, which will give you this expression sin B cos A plus cos B sin A. And this is definitely equal to this length. So this is the second proof. This is also visual in a way, but by using lengths. Now I would like to go into the third proof, which follows from a very interesting mathematical formula, I think, which is some people say it's the most beautiful formula in mathematics, and also I feel it's very beautiful in a way, and it connects a lot of different parts of mathematics. So we are going to use Euler's formula. E to the power minus x is going to be cos x plus I sin x. I'm not going to go into the proof of it. There are proofs. There is this very famous proof by using the infinite series, and so you can. I'm not going to go into that. I'm just going to show you that this formula also contains the knowledge of sin A plus B and cos A plus B formulas. Of course, it should be, because this is like a very very educated formula. Okay, so what we are going to do, it's very simple. You take e to the power minus ix, then you take e to the power minus iy, and then you multiply these two expressions. So then you are going to use also law of exponents here, and its validity in complex numbers also, which I am not particularly very sure of. I'm still thinking about these things, exponentiation. But if the law of exponent can be used here, then you can club these things together and get e to the power ix plus y, and then you can algebraically multiply these two terms to get this and this here. Now you can in LHS you can break it down to cos x plus y plus I sin x plus y, and not only sin x plus y, you also get the formula for cos x plus y here if you equate the real and the imaginary part. So yeah, this is pretty interesting. As I say that this is a very educated formula, so it will give you more than what you want. So you see that we have the expression for these two things, these two formulas also. By the way, you can always using one of these you can calculate the other one, because sine and cos are complementary in a way. So but still you see the beauty of it. It gives you the results in a very balanced way. Well, thank you for watching. Have a nice day.